The most common type of motion in machines is the rotary motion. Almost any moving machine will have parts that are rotating. Motion is generated by maybe an engine, a wind or a water turbine as a rotational motion. Then the motion gets translated further in the machine using gears or pulleys. All these parts are rotating parts. These rotating elements have a lot in common. Any rotating shaft has to be supported at a bearing point, or most commonly 2 bearing points. And then you have the section of the shaft where the rotation is needed for the function. For example, there is a gear mounted on it. If you want to use the tolerances that we know so far to control this rotating function, you will have to use straightness to control the straightness of the center line of the rotating section, also cylindricity to control the surface, and also concentricity to control the center line of the rotating section, and the bearing section are concentric. But what if I told you that there is one tolerance that you can use to combine all these together? This is the runout tolerance. Let's look at how the measurement of a runout tolerance is done. This part here has 2 cylindrical sections. The first one has a diameter of 20 and we call its center line datum A. And then we point at the surface of this other cylinder with a runout tolerance, which looks like an arrow, with a value of 0.1 with reference to datum A. The way this measurement is done is by fixing the center line of A as a reference in the measurement. A dial gauge is then pressed against the surface of the tolerated surface. When the gauge is pressed against the surface, I set the value to 0. Then I start rotating the part around the axis of the bigger section, and I measure the height again. This way, the dial gauge measures the difference in height between the different points of the surface while it's rotating, with reference to axis A. As long as the difference in height is smaller than the value of the tolerance, then the part passes the inspection. This difference in height could be resulting from a concentricity error between the 2 cylinders. So one end of the surface is further to the dial gauge than the other one. Or it could be a result of a cylindricity or circularity error. Maybe it was not a circle, but it looked like that. I will still get different readings when I rotate the part around A. So, using the runout tolerance, I cannot know where the deviation is coming from. I don't know what is causing the error, but I know that there is an error that will affect the rotating function around A, with a value, for example, of 0.1, regardless of the origin of this error. For you, if you are a designer, why would you pay so much attention to the source of the error? For you, the function is what matters. But if you are in manufacturing and you find a part that is reading 0.2 out of tolerance, using only the runout measurement, you cannot find the source of the error in order to correct it. You would have to measure concentricity, circularity, straightness, and so on individually. What I measured now is the circular runout. If I now want to control not only the runout on one circle on the part, but on all cross sections, then I would have to use the total runout tolerance. This is similar to the difference between circularity and cylindricity. Using circularity or circular runout, you still measure in different cross sections, but the result of each cross section is evaluated independently from the other cross sections. But if you use the total runout, which symbol looks like this, 2 connected arrows instead of 1. The measurement has to be done on different cross sections, and all the results has to be evaluated as if it was one cross section. So the difference in height is now evaluated between all the points on the whole cylinder. not only on one cross-section. Not only we can measure the runout on a cylindrical surface, but also we can measure it on a plane. We are still rotating the part around a cylinder, so the datum is still a cylinder, but the measurement itself is done on a planar surface. Let's look at our part one more time. If I use now the small cylinder as a datum, datum B, and then I point at this surface and say, this surface has to have a runout, in this case a total runout, of 0.1 to datum B. This means that I have to fix my part on the datum diameter, and the gauge will be pressed against the toleranced planar surface. Then I start rotating the part around B and start recording the difference in height between the points of the planar surface. And because it's a total runout, a total planar runout, I have to measure on different distances from the center point to take points that are distributed all over the surface in consideration. Of course, the difference in height between any two points has not to exceed the value of the tolerance zone. A common error with the runout tolerance is pointing at a dimension line instead of pointing at the surface. This is wrong, because the runout tolerance can only control a functional surface. So these were the different runout tolerances. In summary, you have the circular runout, which is measuring one circle on a cylindrical feature. Then you have the circular total runout, which is measuring points distributed all over a cylindrical feature. Then you have the planar runout, which measures points that are distributed on a circle on a planar surface. Then there is the total planar runout, which measures points distributed all over a planar surface. So, do we have to use the runout tolerance, or should we split it into its basic components? Try to use the runout tolerance whenever possible, because it will make the parts cheaper while satisfying the same function. If, for example, the manufacturer produces a part with a runout error that is out of tolerance, they have the freedom to correct it either by correcting concentricity or by correcting cylindricity, or by correcting both of them in the same time. So they can always choose whatever for them is easier to correct, and they will go ahead and do it, which makes the parts cheaper. But if each of the tolerances were specified individually, then this choice, this freedom, is not really there anymore.
If you found this video helpful, don't forget to give it a like and drop a comment below. We'd love to hear your thoughts or questions. And if you're into leveling up your skills with expert-led content, hit that subscribe button and turn on notifications. For full courses, downloadable assignments, and certifications, head over to Excedify.com. Start learning smarter today.